I'm recording.
I don't care.
Okay. All right. So,
Thank you.
thankfully, we are finished with covering Chapter 2. And Chapter 3 is a very brief one by comparison.
I'm good. I don't know. This is a long book.
And so now, instead of first order nonlinear PDEs like we have been doing, we're doing second order linear PDEs. So this will be like the first part of Chapter 3, very short sections here, and then we'll wrap this chapter up on Monday. All right. I guess I should say that today's lecture is powered by Starbucks. Thanks, Ellie.
Woo!
So I might have a little more energy this time.
3, 4.
What?
Adam's at Starbucks today. Say like literally half the class has it today.
That's what? Oh, Starbucks. Oh.
Mhm.
Okay, good. So we're all powered by, half powered by Starbucks. Okay, so look at the general form, and I could be a little more specific than this. We're only dealing with two independent variables, so just x and y. So we have some differential operator L applied to the solution U, and it'll have this form: AUXX plus 2BUXY plus CUYY. So those are second order partial derivatives. And then we have some first partials: dux plus duy plus fu equals g. Okay. Now, one thing that's a little odd about this, I've actually written this equation on the board before, except this one is slightly different. I want to highlight the 2 here, because the textbook author put that 2 in there, which is not, I don't normally see that in PDE books. And he claims it's put in there for convenience. And I guess it does make things certain things convenient. So for instance, like, okay, when the same topic is covered in 417, 517, that 2 is not going to be there, so formulas will be all different. And as I go through this, you're going to think that I'm getting a quadratic formula wrong, when actually I'm not. So I just want to warn you about all that. It's all because of a fault of that 2. And I would prefer not to have it, because I have to change my notes around it. But I wanted to be consistent with that dang book, which I never want to use again.
Really?
So like
Really for you?
Yeah. What?
UXY is for XYs and YX, right?
Yeah, yeah. Yeah, so you can think of it as being like that.
So like for future, will it be there or not?
I'm going to use it. I get it. Yeah. So in this class, the 2 is there.
Okay.
So
They're saying they'll have the same constant B?
well, that's it, because compared to anyone else, any other source, this B is their B over 2. Yeah, so it kind of throws things off. Okay, so for instance,
If they have to be equal, so they have to have the same constant.
yeah, so Haley, if you see this topic in 517, that B's not going to be there, everything will be different. So.
Oh, he doesn't really. I don't know.
Oh, okay.
Never mind. Go ahead.
Good point. Now, we're most interested in this part, but it has the second order partial derivatives. So I'm going to call this L sub 0 of U, and that is called the principal parts of the entire operator L. This is the one that really determines the behavior of a solution, because depending on the coefficients and how the PDE is classified, it only depends on that principal part, and the behavior of solutions in these different cases are completely different. Okay, so I'm going to define this notation delta L, which is B squared minus AC. So before your antenna go off and say, shouldn't that be B squared minus 4AC? The 2 messes with all that, because if I did the proper discriminant, I'd have 4b squared minus 4ac, and you toss aside the 4. So,
Right.
yeah. So this is
Target.
from 2b squared minus 4ac. Yeah. So, yes, that's why all class long you're going to be thinking I don't know the quadratic formula. So, okay. So this quantity here, which is a function of x and y, in many cases there'll be a constant, but it's a scalar value quantity. This determines how a PDE is classified. So let's write down the classification, and it covers very briefly at the very beginning of the course, but we're going to focus more on it now. So this discriminant is, if it's positive, then the second order PDE is said to be hyperbolic. If it is equal to 0, it is parabolic. And if it's negative, it is elliptic. Okay. Now, as I mentioned last time, I'll refresh your memory. These names have nothing to do with how the solutions of a PDE actually behave. There's nothing conic section-like about them. But if you think about a typical quadratic function, ax squared plus 2bxy plus cy squared, this discriminant would determine whether that equation set equals 0 describes a hyperbola, a parabola, or an ellipse. That's where the names come from. It's just that these distinctions of whether this discriminant is positive, negative, or 0 drastically affects how the solutions of a PDE behave. And so what's going to happen as we get into later chapters, we're going to spend a lot of time on a standard hyperbolic PDE, the wave equation, a parabolic PDE, the heat equation, an elliptic PDE, Laplace's equation, that all have fundamentally different behavior. So this gives us an easy way to classify which case we're talking about and names that we can relate to by thinking in terms of quadratic equations. Okay. Now, but what we're going to do in this chapter is about more than just classifying PDEs. So if I give you any PDE, no matter how complicated, you can determine whether it's hyperbolic, parabolic, or elliptic. And if the coefficients A, B, and C are not constant, you may have a situation, this will come up in the homework for this chapter, where PDE is hyperbolic in one region, x, y, and say parabolic in another, and elliptic in another. A PDE is allowed to change types, which really complicates things. But once you've classified a PDE, what we really want to do is try to transform it. So that's the real goal, to transform it into a simpler form. But the thing is, how do you know what simpler form you can transform it into? That's why you need the classification. So, so the idea is, now, again, I'm restricting this discussion to second order linear PDEs. As a canonical form. In other words, a drastically simpler form of a PDE, one that we can actually try to solve. But the question is, which form are you going to use? It depends on whether it is I'll make a chart here. So if a PDE is hyperbolic, then the canonical form you could use is and I can use new variables. Instead of x and y, I use c and eta. Alright, and I'm only focusing on the principal part. That's why I'm putting these dot dot dots for the non-principal terms, because I genuinely don't care about them. But this is where the interesting behavior comes from. If it is then you have one second order derivative. Actually, you could use u xc or u eta eta. You can pick which one you want, depending on the transformation. But the point is, you have just one second order derivative, and which one it is, it makes a big difference. And then finally, if it is elliptic, then you have both partial derivatives that have the same variable. So the mixed partial derivative is out, but the other two remain, and you can have them with equal coefficients. So when we go to later chapters and we study wave equation, heat equation, Laplace's equation, in order to figure out how to solve them, we're just going to work with the canonical forms, because that tells us all we need to know about how to solve second order linear PDEs in general.
So for heat equations, we have to only use the mixed partials?
This is wave. There's a wave equation, we only use mixed partial. Yeah, so
wave equations are hyperbolic.
Wave
equation
heat is parabolic.
So
And Laplace's equation
okay.
is elliptic.
So for heat, we use only the double derivative.
Yeah, and only one of them. Yeah.
Only one of
So
them.
Yeah.
mixed, one type, two types.
Yes.
So is it UXX or UYY or something like that?
Yeah, either one. And the thing is, you're going to have like some first order derivative
Yeah.
that might play the role of time, for instance.
Right.
Yeah. Okay. All right. So now the question we need to ask is, now that we have canonical forms for each case, we need to know, how can we transform a given PDE into a canonical form? And this is why it's important to classify the PDE up front, because if you try to do the wrong, you try to transfer it to the wrong canonical form, you find you won't be able to. Like something will go wrong with a computation. So you need to know what you're getting into before you start. Okay. So what I'm going to do is talk about how you transform PDEs in general. Like if you do a change of variable from xy to xc eta, what are your new coefficients in the general case? And then we'll focus for today in the hyperbolic case, and then on Monday we'll deal with parabolic and elliptic. Okay. So to carry out the transformation from the independent variables x and y to the new independent variables c and eta, it's a huge, huge chain rule exercise. So first, your first partial derivatives. So that's not so bad. So du dx is du dxc, c dx plus u eta x, and then similarly for du dy. Alright, so you can see without too much trouble, I hope, why that works. What you can replace your first derivatives with to get derivatives with respect to the new variables. Now, when you go to second derivatives, that's where things get really ugly. Okay. So, for instance, suppose I want to take my ux up here, and I want to differentiate that with respect to x again. So what's going to happen is, I I'm going to, so I'll start on this term right here. So I'm going to have du dc with respect to x times this again. But du dc and then cxx. Product rule. That just comes from a first term. And then similar for the second term. Du d eta with respect to x times eta x plus du d eta untouched and then eta xx. Okay. Unfortunately, I'm not done because these two terms are completely worked out, but now I have to carry out differentiation of like du dc with respect to x. But how do you differentiate with respect to x? Use this. Differentiate with respect to. So this term gives me two more. So these terms are like breeding. As soon as we're going to overrun the board. So we have u c cx from here, and then one that's already sitting here. So that gets squared. Plus a mixed partial, u c eta x cx. Okay. So, all right. So the number of terms is growing, but I still have this one. U c cxx, and then similar process for this. I have u eta x. Oh, sorry, u eta xc xcx eta x, but that's the same as this term. Bless you. So I actually have two of those now. So that saves me a little bit of space. And then from the other term here, I'm going to get plus u eta x squared, and then I have this. So I have 5 terms altogether to describe second partial derivative with respect to x. So that's pretty ugly. And then you carry out the same process to get expressions for uxy and uyy. It's all in notes. I'm not going to write it because, as you'll be able to see, the longer I write, the less like x's the x's will be.
Squigglies.
Squigglies, yes.
You should just start making it like squiggly, like a coil, just to distinct so we know what you're talking about.
I try.
Well, because that's what
But
it starts to look like anyway.
I get squiggly fatigue. So, all right. So what you can do after you work out uxy and then uyy in a similar fashion, then you can plug these back into your PDE and then rearrange. So, okay, so sub all of these into your PDE, and then you group terms by whatever partial derivatives you have in the new variables. Okay, sometimes I can make this look semi-decent. Trouble is,
I'm not like a cute squiggly, just like curve, like.
like what?
Like
that?
Yeah, just because we know what or I know what you're talking about.
I can't. It just feels wrong. Okay, so these 3 partial derivatives for second partial derivatives, as well as the first partial derivative. So group everything by that, and that way you can get the new coefficients. Which I'll call A bar, B bar, etc. Okay, so now after doing all that, I can show you what is your new PDE. And the idea is, now that you'll have formulas for the new coefficients, you can try to get a canonical form by setting certain coefficients equal to 0, like in your principal part. And And that helps you solve for the change of variable that you need. Okay. Yes, we did. Okay. Except all the expressions are different. They're different because I didn't have a 2.
I was gonna say, wait, you just threw a 2 in there.
Yeah. Yeah, so I had to go, I actually dug up those old notes because I was lazy, and I just made the appropriate changes.
Oh, I didn't take this with you.
Okay. So my new PDE is A bar U squiggly squiggly plus 2, the 2 persists, U squiggly eta plus C bar U eta eta plus D bar U squiggly plus E bar U eta plus F bar U is equal to G bar. Okay. Now, so what are the new coefficients in terms of the old? So for instance, A bar, B bar, C bar can be expressed in terms of the original A, B, and C. And so we have A squiggly x squared plus 2b squiggly x squiggly y plus C squiggly y squared. So notice it's a quadratic function in terms of the derivatives of C with respect to x and y. And in fact, C bar has the same kind of form, except it's eta instead of C, which helps a great deal in terms of coming up with a transformation. Okay. Whereas B bar is much different. It has mixes of C and eta. So you have A x eta x plus B, and then mixed cases, so squiggly x eta y plus cy eta x plus C cy eta y. Okay. And then the less important coefficients for first order derivatives and lower. So we have, now, so D and E bar are for first derivatives. They still depend on A, B, and C. And the second partials of C and eta. So the D bar coefficient depends on C. Plus D Cx plus E Cy. Okay, and then E bar is actually the exact same thing, except instead of C, it's eta. Okay. And then finally, the coefficients for F, G do not change at all because they don't involve any partial derivatives of U at all. Okay, so the next thing is, there are certain homework problems where you're given a PDE and you're asked to come up with the new coefficients. So at least now you have, no matter what kind of PDE is, hyperbolic, parabolic, elliptic, you know what the new coefficients are once you have a change of variable. Okay, but at this point, the idea is generally you don't have a change of variable known up front. Instead you have a goal. It's like if you know, suppose you know that your original PDE is hyperbolic. So the new PDE will also be hyperbolic. I'll explain that in a moment. Why? But only B bar that's the only thing in your principal part. So you want to make sure that you choose C and eta so that these two coefficients, A bar and C bar, will equal 0. And I will get into that in a moment for hyperbolic equations. But first, still talking about the general case. Yeah, I'll stay in this board. If you were to express A bar, B bar, C bar in terms of A, B, and C, but not as I've written them here, but in terms of matrix products, there's actually a relatively simple way to do that. So you could say that, actually I hope this is still, okay. So if you arrange them in a matrix, a symmetric matrix where you have A bar, B bar, and C bar arranged in this way, you can actually write it this way. We have squiggly x, squiggly y, eta x, eta y, times the original coefficients times this same matrix again. Squiggly x, squiggly y, eta x, eta y. Okay. Now, what does this say in terms of how the new PDE that you have here is to be classified? Well, the way you classify is by the discriminant, this delta that I wrote earlier. So I'm going to call this operator L bar, just like I called the operator L in the original. So the classification of L bar, well, that's the determinant of this matrix. So it's A bar, C bar, minus B bar squared. Well, actually, it's minus this, because I had written the other way. Okay. There. Okay. So the determinant of this matrix, so that's what I'm trying to say here, but as I've told you, I'm quite brain dead today. So all of this is the determinant of this matrix. It's just that the determinant of this matrix is the opposite of the sign of the discriminant of classification. Okay. Now, here I have this matrix expressed as a product. How do I get the determinant of a product of matrices? For those who know linear algebra. What?
Can't you just, you do something with the two determinants?
Yeah, you multiply the determinants.
That's fast.
Okay.
So I was gonna say.
Sorry. Okay. All right. So, well, that's the determinant of this matrix. So that's going to be squiggly x, eta y, minus squiggly y, eta x. And this one too, so we square that. And what do we have here? Well, that's AC minus B squared. So what that means is, but this is equal to minus the discriminant of L. So to simplify all of this, I could say that the discriminant of L bar, after I drop all the minuses, is the Jacobian squared of a change of variable, because that's what this is. This determinant is the Jacobian of a change of variable. So, all right, times the discriminant of L. Now, the key here is that the Jacobian is squared. So that part's going to be positive. So what that means is, okay, unfortunately I've run out of room on this board, but okay, I don't want to switch boards yet. But at least this will look more sensible in your notes than it will on the board.
That became negative, and then you said you could take the product of the determinants.
Yes.
Because of
okay.
matrix product.
Because the determinant of a product is a product of the determinants.
Okay.
Yeah.
Okay. And then times that determinant equals Jacobian squared.
Yeah, because this one appeared twice.
Negative on both sides.
Yeah, negative on both sides, I just dropped that. Yeah.
Okay.
Okay. Yeah. So what that means is the classification of a PDE is invariant under a non-singular, in other words, invertible, coordinate change. Because even though the value of a discriminant, like the numerical value, will change, the sign is not going to change because it's multiplied by j squared. So the positive number won't change the sign. So in other words, if you have a hyperbolic PDE, you do a non-singular coordinate change, the new PDE comes out that this one is still hyperbolic. So it preserves that type. And that's very important because that means you can take a hyperbolic PDE, for example, and transform it into another hyperbolic PDE by whatever change of variable you need to get it to a canonical form, the appropriate one for hyperbolic equations. But that's why you need to know the type up front so that you can do the proper transformation. Because if you have a hyperbolic PDE and you try to transform it into a parabolic canonical form, you can't. Something will go wrong. Okay. Now to see, now I don't expect you to see how I got this factorization from this, but I will give you just a touch of linear algebra to give you an idea as to how. This is about quadratic forms, at least in 2 by 2 case. If you have a matrix like this, expression like this, X transpose AX, where A is a symmetric matrix, and X is some vector, that can be written as a sum over all indices I and J, Aij, Xi, Xj. So this is true for any n by n matrix and n vectors, but here we're just using it in the 2 by 2 case. And you can see how, for instance, especially these expressions for A bar and C bar, how you can see this as being like this formula in the 2 by 2 case. So that's where this comes from. And if I have Y transpose AX, so the two vectors are different, then I have like Xi, Yj. So if you recognize that this sum can be written as this kind of form, then you can figure out this factorization on an element by element basis. I know it doesn't really cement everything, but this gives you a way to convince yourself that this is correct. In case you're not convinced already, but because you should not take my word for these things. Okay, so now
This whole time I've been thinking, you probably don't know the quadratic formula. Sorry, I couldn't help it. Okay, go ahead.
yes.
So for the second order PDE, like, so when if you check for transversality, for these, would you have to use the Jacobian squared, or or you just use Jacobian?
Transversality, like we talked about, is a like that's really a first order equation.
First order. Oh.
Yeah. I mean, okay. Yeah. So what we're going to make sure is when you are coming up with a change of variable to go from one PDE to another, it's a similar concept. So transversality for as applied to making sure a first order PDE is solvable, it's a similar concept to checking if your coordinate transformation is non-singular just because you're looking for an invertible change of variable. So it's really that generic concept we're dealing with. It just applied in two different situations.
Well, then you're saying non-singular, so it has to be invertible, which means
Right.
the Jacobian has to be,
Non-zero.
Non-zero, not
Yeah.
greater than zero.
Yeah.
Non-zero. So, no matter what, if b squared minus ac is still 0, it's like this, parabolic, right?
Yeah.
Parabolic.
Parabolic.
So, yeah. And if it's less than 0, it's elliptic.
Yeah. Yes.
But regardless, the Jacobian will be non-zero, right?
Yeah, we have to make sure the Jacobian is non-zero because then, if you have a singular change of variable, that allows a PDE to change type. and we don't want to do that. So at least, as long as you construct carefully your change of variable to make it invertible, you know your PDE is not going to change type on you.
When do we have to do the singular thing?
Well, you wouldn't want to.
Okay.
Yeah. I mean, 'cause that opens up a whole can of worms. You just don't want to go there. Yeah. So don't. Okay. So now we can focus. So for the rest of today, we're going to focus on just a hyperbolic case. All right. Okay. Actually, I hope I have better chalk than this. Not really. Okay. So we have a given PDE, and we check and find that it's hyperbolic. That's its classification. And we want to transform it into a nice simple hyperbolic PDE, but once in canonical form. How do we do that? We need to come up with a change of variable, the xy going to exceed eta, that will allow us to happen. Okay. So what we want is a bar and c bar to be 0. Okay. So if we look at the formulas we have, I'm going to take a formula that's written over there for a bar and c bar, except I'm going to divide through by like cy squared in the first case and eta y squared. The idea is I want c, the original c, to be by itself. So I get something like this. A cx over cy squared plus 2b cx over cy first power plus c is 0. So it's the same formula for a bar, I've just divided through by something. And then, and this is from requirement that a bar is 0. And then from requirement that c bar is 0, I have a similar thing, except it's just with eta. I can't help but notice how when I have a formula involving eta, I write it much faster. Okay. So the convenient thing here is, if we think of cx over cy as being a new variable, and eta x or eta y as being a new variable, I have the same quadratic equation in both cases. I only need to solve this once. But I get two solutions. So
in the first instance, you're dividing by cy squared, and
yes.
second, you're dividing by eta y squared.
Yes. Okay. All right. So I can solve this quadratic equation, get the two solutions from a quadratic formula, and then I can do the following. I'm going to say that cx over cy is equal to one of the solutions. Now choose this one, minus b minus square root of b squared minus ac over a. And now I can see that it's like a morphed quadratic formula. So it's just going to cause confusion.
I hope I don't teach it wrong next chapter.
Yeah. Well, actually, I'm worried about those of you who are Math 500.
Well, you don't have the
Especially you have to drive the thing.
You
I
don't
had to
have
do that. Yeah, I had that section.
you don't have the plus minus like that. You just have the minus.
What?
I mean, negative b plus minus. So you just chose the negative.
Yeah, because I also have the other solution. I have eta x over eta y is the other solution, minus b plus. Okay.
But then, do you just arbitrarily choose that?
Yeah, actually, I made the choice of which one is minus and which one is plus based on how the textbook did it.
Okay.
In fact, in my notes from 517, I had it the other way around.
Okay.
So, yeah, I guess the textbook is very contrarian.
Yeah.
It's really annoying.
Oh, I did.
We're talking about, sorry, we're
The-
talking about driving
The quadratic formula.
Oh, okay. Oh, yeah. I guess you two are in the same boat.
I don't. Yeah, but we don't actually do that in 101, like in class.
Oh, that's interesting. Oh, you just don't cover that part?
Well, they don't need to know it. There's no
Yeah,
point.
I didn't think so.
There's so much other stuff you have to cover in class.
Yeah.
There's no point. But then I had a student ask me where it came from, so I had to do it on the spot.
Oh, okay.
So
So you never know.
yeah, I was like, really?
Yeah.
Like
Actually,
that's mean. They're like, will you make us come to the board? I'm like, y'all's are easier than
things,
that.
now I can't help but be reminded of when the quadratic formula actually was mentioned in a Family Guy episode. And if you don't know what I'm talking about, I better not talk about it, but you can search for it. So,
What?
some of you might know.
That used to be an exam question in
Yeah.
like back in school. I got the direct.
Really?
Are you searching for it now?
Yeah.
Okay.
I won't forget.
Does anyone know who I'm referring? What I'm referring to?
I don't watch the show.
Okay.
Oh, I'll find out.
She's dumb.
Okay.
The Family Guy episode.
Don't play it here.
Now they have no one to take notes.
Okay.
Haley takes the notes for Abdullah, the extra stuff he doesn't feel like writing down, so now he has nobody to do that.
What?
They're both watching the video.
No,
Okay.
I mean, no, not that was just once. It was not even no.
Okay.
Instruction part for it.
Anyhow. Okay. So the idea is, since these two, so these expressions, xcx over xy and eta x over eta y, these are known. So at least we have some information about the change of variable. And the thing is, if we look at coordinate curves, c equals constant. That means that change in xc, which is cx dx plus cy dy, is going to be 0 because c is constant. And then the other coordinate curves in the new variables, eta equals constant, we get the same thing. The eta, which is eta x dx plus eta y dy, is also 0. And the reason why this helps us is now we can rearrange these to get useful ODE. So I can say that dy dx, from a first one, dy dx is minus cx over cy. And I know what this is, so it's over there. So I have b plus square root of b squared minus ac over a. So I can go ahead and solve that. That's just a plain old ODE. And then I also have a similar one for eta. So dy dx is minus eta x over eta y. So that's going to be b minus square root of b squared minus ac over a. Okay. So once I solve these, I know something about xc and eta. Okay.
I have a question.
Yeah.
Where you put that eta and z is constant, are those like, are they always constant, or are these like if scenarios?
Well, the idea is, let's look at it this way. In x and y, you think of, you have your horizontal and vertical lines. X equals constant, y equals constant.
Yeah.
And now we're doing the same thing in the new variables to try to, basically we're trying, if you think in terms of throwing a grid over your xc eta plane, and you want to see how that will relate to curves in the xy plane to see what a change of variables is. So xc and eta are actually variables, but to try to solve for what they are in terms of x and y, we look at the coordinate curves. So that's all we're doing. Yeah. Okay.
Now,
Okay. Now the thing is, b squared minus ac, we know this is positive. So we know we're going to get two distinct solutions in a hyperbolic case. Whereas what would happen if this was parabolic? So far, I haven't really used the hyperbolicity yet.
no real solutions.
We want.
One solution. These would be the same. So I could only have. So what happens
Oh,
is.
they would equal each other.
Yeah.
Well, b
Yeah.
squared
You
minus
have two
AC
different that go
Yeah.
is 0.
Yeah.
So you get b over a.
Yes. And I could just solve out one.
Mm-hmm.
What about if it's elliptic? No real solutions. If you wanted to allow being complex, you'd have them, but And so what that really means is, okay. All right. I'm going to check my notation here. So, so what you get is basically a one-parameter family of characteristic surfaces. All right, so I should say family of. Okay, just because you're able to solve for infinitely many X's and infinitely many Etas. Because here we're assuming that X is constant to get this equation and Eta is constant to this equation, but they can be any constant. Okay. Okay. On the other hand, in the parabolic case, you only get one characteristic surface. And that's either Xc is a constant or Eta is a constant. Okay. And then if it's elliptic, there's no characteristic surface. Okay. By characteristic surface, I mean it's a surface that across which the solution can have a discontinuity. Kind of like in first-order equations, we had characteristic curves that could be used to transport discontinuity in the initial data. So, so what you can have is, for a hyperbolic equation, you can have two infinite families of surfaces that can carry discontinuities. And we're going to see that when we study a wave equation, we can have propagation discontinuities in two different directions.
Both directions.
Yeah.
So hyperbolic,
Right. Whereas parabolic, that you don't have that kind of propagation. And then what happens here is you have propagation at finite speed. Here you have propagation only at infinite speed. So diffusion is thought of as being instantaneous. And then here you have no propagation at all in the elliptic case. Okay. All right. So because, for instance, in the hyperbolic case, if you have initial data that's only a blip on your real axis, for that blip to have an effect elsewhere along a real line, it takes time to get there. So, so you don't really have anything yet first until enough time passes for that blip to propagate one direction or the other.
Yeah, like waves, right?
Yeah, like waves. Heat equation, if your initial data is a blip, as soon as time becomes positive at all, that blip affects the entire real line. Now, maybe only to a small extent, but it's felt instantaneously everywhere. Now, I know that, of course, real diffusion doesn't behave that way, but it's close enough of an approximation where it does. And elliptic, there's no such propagation, either finite or infinite speed. Okay, let's see, how are we doing on time? Okay. All right. Okay, so now, actually, I should say, I messed up earlier. This is a two-parameter family of characteristic surfaces. Here you only have one parameter family because you can choose one of these variables to be constant, and that's all. And then here you get nothing. Okay. So now what I'll do is an example of how you transform a hyperbolic PDE. I have, 20-something minutes, so that'll work. So like for instance, with a wave equation, you have two families of characteristic curves. You have like x minus t is equal to any constant, and then x plus t is equal to any constant. Okay. Okay. Now, actually, actually, there's a sort of a holdover from my old notes where I say surfaces here. We're in 2 dimensions, x and y. So, where I said surfaces, I really should have said curves. Whereas if you're in 3 dimensions, surfaces would be the correct term. But we're sticking 2 dimensions. So sorry about that. I should have said curves. I guess I could say hypersurface, and then I'd be right all the time. So.
What the heck is that?
So that should be.
Hyper.
It's an entity of 1 dimension less. Like, okay, and if you're in 2 dimensions, a hypersurface would be a line. If you're in free space,
It was plane.
if you're in free space, you'd have a hyperplane, 2-dimensional entity. So, yeah.
I've just never heard that term.
Okay. All right. All right. So do an example of a hyperbolic PDE. Y squared uxx minus x squared uyy is 0. So A is y squared, B is 0, C is minus x squared. So B squared minus AC is x squared, y squared. Okay. Positive, at least as long as we're not at the origin anyway. So we're kind of steer clear of that. But we'd like to get this into the form u exceed eta is equal to 0. So that would be the canonical form for this simple of a, because notice we only have a principal part. All the lower order terms are gone. Okay. So that's what we're shooting for. So carrying out the procedure I described earlier, we could just jump right in and get directly to a quadratic equation. We have cx over cy is, okay, so we have minus b minus discriminant over a. And when we work all that out, we get minus x over y. And then eta x over eta y is just going to be x over y. So now this leads to the ODEs. dy dx is equal to x over y. So this is for c equals constant. And then dy dx equals minus x over y, or eta equals constant. And fortunately, these are relatively easy ODEs to solve. These are separable. So for the first one, I have y dy equals x dx. And for the other one, I have y dy is equal to minus x dx. So all I have to do is integrate both sides. So if I integrate both sides of this, I get my plus c is going to be xc. So xc is going to be y squared minus x squared. And then for the other one, I integrate both sides. I say eta is equal to y squared plus x squared. Because in both cases, you get a constant of integration. So that constant of integration, you treat like a variable. Xc in this case, and eta in this case. So this is where you keep in mind which variable is constant to figure out your formulas for xc and eta. So now we have our change of variables. So now I can write down the coefficients of a new PDE. But the thing is, we don't have to do all of them because A bar and C bar bless you, are already 0 by design. So we're not going to bother computing those. The interesting coefficient is actually B bar. Let's see, actually, oh, you know what? Sorry. I'm not going to be able to reduce all the way to that conform UXC 8 equals 0. There's still, that's the principal part that I'll get. There's still going to be lower order terms. I know that the right side is 0 because the original left side is 0. That's the only thing I know for sure. Okay. So now, my formula for B bar, to get my principal part, is the original A, Cx eta y, no, Cx eta x, plus B, Cx eta y plus Cy eta x, plus C, Cy eta y. So once I fill in everything, well, B is 0. A is y squared. And then Cx is, I go take my partial derivatives from here. So that's minus 2x. And then eta x is plus 2x. B is 0, so all of that's gone. And then C is minus x squared. And I have Cy is 2y. And eta y is also 2y. So this is where I get the formula for my new coefficient. So once I combine all of that, I'm going to get minus 8x squared y squared. So that is the coefficient. Yeah, so I'm going to have a B bar up here. That's minus 8x squared y squared. Although if I really wanted to, I could divide by it and have a simpler principal part. But especially because my equation is homogeneous anyway. So any questions about where the new B bar comes from? These are just from formulas that I had on this board earlier. So then, as for new coefficients, F bar and G bar are already known to be 0 because they weren't in the original. The only thing that's left is D bar and E bar. So D bar is, actually it's kind of a mess, A Cxx plus 2B Cxy plus C Cyy plus D Cx plus E Cy. Although much of this is 0 because B, B, D, and E were all 0. So that helps a great deal. So the only thing I have is A is y squared, and Cxx is 2. And then I have C is minus x squared.
Would it be negative 2?
Yes, I was looking at the wrong line. Okay, yeah, minus 2. And then I have Cyy, which is positive 2. So what I get in that case is minus 2x squared plus y squared. And then similarly, E bar, I won't repeat the whole thing here, but that's going to be 2y squared minus x squared. Okay. So now I can put together my new PDE. Okay. All right. new PDE is minus 16 x squared y squared. Because remember, it's 2b bar, so I multiply by 2. U c eta minus 2 x squared plus y squared u c plus 2y squared minus x squared u eta 0, except I'm not done. Because I started with a PDE that was only x and y, coefficients in terms of x and y, partial derivatives with respect to x and y. Now I have partial derivatives with respect to c and eta, but I have coefficients that are still in terms of x and y. So I want to change all that. I want to express everything in terms of new variables. So if I go back to my change of variables, I have c is y squared minus x squared, and eta is y squared plus x squared. So what I'd like to be able to do is express x and y in terms of c and eta. I want to invert this change of variables. However, I don't want to invert it entirely, because notice wherever you have x and y, it only appears as x squared or y squared. So I don't need x and y. I need x squared and y squared. That would be enough. So what would be an easy way to get x squared or y squared?
Solve for the other one?
What?
And solve for the
Add or
other
subtract the equations. So if I add them, I get c plus eta is equal to 2y squared. And if I subtract them, so I would get, actually, if I take the second minus the first, so I'd have eta minus c is equal to 2x squared. So if I go ahead and plug these into here, so for instance, I'm going to borrow 2 factors of 2 from here, so I can get minus 4.
Eta plus
2x squared is eta minus c. And then I have 2y squared is eta plus c. U exceed eta. And then I have minus 2x squared is, so that's going to be c minus eta. Okay. Then minus 2y squared.
So you just do eta, right?
Oh, sorry. Yeah. Like I said, brain dead. Yeah, I have these expressions right here. So, okay, so that's minus 2 eta uxc plus y squared minus squared 2xc u eta equals 0. Okay, and then I can just simplify the last part, so I get 4 c squared minus eta squared u exceed eta minus 2n u exceed plus 2 exceed u eta 0. And actually, I can go ahead and drop a factor of 2 throughout. Okay. Let's see. Actually, what I have in my notes is it's the exact same thing, only it's negated. Okay. So now I have. So this is my final form of my new PDE. Okay. So any questions about that exhaustive process? Okay. So because we only have one second partial derivative, this in theory would be much easier to solve than the original form. I should mention though that once you have it in this canonical form, and this is actually something that's not even in the 606 textbook, it is found in the 517 textbook. An alternative transformation. Once you have it in this form already, where you have this principal part, if you let alpha equal c plus eta and beta equal c minus eta, what happens is the partial derivative in the principal part, c eta, becomes u alpha alpha minus u beta beta. And the reason why this is significant is this is basically the form of the second order wave equation, which we're going to study in the next chapter. Although actually what we do is once we have this kind of equation, wave equation like uxx minus utt, we actually do we do the opposite of this change of variable to get it into this form to come up with an easy way to solve it. So it's kind of go back and forth between the two forms. But at least in this case, the coefficients are just negatives of each other as opposed to the original PDE that was hyperbolic but had different coefficients for uxx and uyy. So if you make this change of variable to this already transformed PDE,
Is your signs, are your signs right on
I
that?
was gonna ask the same thing.
Is it? Because if you took out a factor of -2, then the first one's right.
Oh,
Then wouldn't it the second two
Or-
wouldn't?
Right?
Hold on, I was making sure, checking against my notes here.
Which one?
Except,
Yeah. Well, you switched
yeah,
them.
yeah, 'cause this is
I'm
eta
totally-
squared minus 6c squared.
Oh, okay. Oh, cool.
Wait,
Sorry
well,
about
hold
that.
on, hold on.
Okay.
Wait, what?
My bad.
If I multiply this out, I get eta squared minus xc squared.
But then
But
the
I switched
negative.
Right.
Or I switched it.
Oh, and so
My bad.
that would have been.
And I forgot I did that.
I was the same way.
Yeah, I've thought about it for a long time.
Okay.
Yeah.
Then you let alpha be that plus that,
Yep.
beta be that minus that, but you have.
I wanted the coefficient to be positive.
Cool.
Yeah, that's fine.
It's gonna
I
give me a
just,
hard
I
time.
got.
I'm sorry.
So I was like, oh my god, my notes are wrong.
The negative thing, yeah.
Okay. So now this PDE would transform into -2 alpha beta, u alpha alpha minus u beta beta, minus beta u alpha plus alpha u beta equals 0. So actually the non-principal part didn't really change by the time it was all said and done. But then we have this wave equation like principal part. So you can use whichever is more convenient as far as hyperbolic equations go. Okay.
Is that a different transformation or just on top of it, in addition?
This transformation.
Like on top of it?
Yeah. Yeah, so you get to this form first and then you do that. And that will at least give you this for the principal part. Who knows what would happen over here? Because we really only care about the principal part anyway. Okay, actually, yeah, I've come to the end. I only have 3 minutes left anyway. So on Monday, we will revisit this, see how we handle changes of variable and canonical forms for parabolic and elliptic PDE. Okay.